Enterprise AI has moved past single chatbots. We're now seeing specialized, autonomous agents spinning up across every department: finance, HR, security, operating at scale. But there is a structural bottleneck. These agents are built on competing frameworks, like LangGraph, CrewAI, and Semantic Kernel. They exist in functional silos, unable to natively communicate. To make a LangGraph agent hand off a task to a CrewAI agent, engineering teams are forced to write bespoke, point-to-point API glue code. This creates a brittle web of connections, known as spaghetti integration. The operational cost here is high. Because these are custom API bridges, whenever a framework pushes an update or a tool requirement changes, those connections shatter, leaving the agents isolated. Direct integration also introduces a security flaw. It forces opaque, black box agents to expose their proprietary internal memory, prompts, and reasoning logic just to pass data back and forth. Large-scale enterprise AI requires more than just high-quality models. It requires a universal, standardized networking protocol designed for autonomous systems. This is the problem the agent-to-agent protocol, or A2A, solves. Originally developed by Google to manage their own massive multi-agent systems, A2A has been donated as an open standard to the Linux Foundation. A2A establishes a new architectural baseline by treating AI agents strictly as opaque microservices. Under this protocol, an agent's internal reasoning, prompt structures, and memory are completely abstracted away. A2A focuses exclusively on the communication contract between the nodes. Rather than inventing new connection types, this contract is built on proven web primitives: standard HTTP endpoints, JSON RPC for messaging, and server-sent events for streaming. This shifts the industry toward a standardized, horizontal, service-oriented model. Effectively, A2A acts as the public internet for AI agents. The first mechanical phase of an A2A workflow is discovery. Before any work can be delegated, a client agent must identify what a remote agent is actually capable of executing. This is solved by the agent card. It functions as a machine-readable business card hosted at a predictable web path, .wellknown/agent.json. The agent card establishes the baseline terms of connection. It advertises the remote agent's identity, the provider, and the specific protocol versions it supports to ensure compatibility. Deeper inside this JSON file is the skills array. This is where the remote agent explicitly lists its discrete capabilities, utilizing tags like triage incident or source candidate. These skills also define the required input modes and output modes. This creates a strict data contract, detailing exactly what formats the agent accepts and returns before any active interaction begins. This structure eliminates the need for hard-coded routing. A client agent can autonomously scrape these cards and dynamically choose the best remote agent for a specific subtask. The agent card replaces a chaotic network of mysterious black boxes with a searchable, deterministic registry of capabilities. Identifying the right agent is only the first step. Discovering a capability does not automatically grant the right to execute it. The agent card also advertises the target's security requirements, natively supporting enterprise authentication schemes like OAuth2 and OpenID Connect. This diagram illustrates the specific threat model of multi-agent networks. Without strict protocols, an ecosystem is vulnerable to authorization creep, where agents slowly accumulate unintended power. Because these agents operate autonomously, an unverified remote agent could execute unauthorized downstream actions if permissions aren't strictly bounded. To mitigate this, A2A requires explicitly delegated, short-lived user tokens. These tokens are mapped to highly specific actions, ensuring a client agent only possesses the exact authorization needed for the requested task. This security by default architecture ensures that organizational boundaries and data privacy policies remain intact, even when complex workflows cross vendor lines. Once authenticated, execution begins. The client agent fires a message send request wrapped in a standard JSON RPC 2.0 envelope. Looking at this architectural map, you can see A2A avoids treating requests as single, blocking API calls. Every incoming request generates a unique, stateful task object. The remote server immediately replies with a distinct task ID and sets the initial state to task status submitted. This design accommodates the reality of agent timeframes. A complex reasoning task or deep research job might take hours to complete, meaning a standard API connection would simply time out. A2A handles this latency by allowing the client agent to subscribe to real-time updates over the connection using server-sent events. As the state transitions to working, the remote agent continuously streams progress updates back to the client, confirming the process is active and preventing network timeouts. If the agent encounters a blocker or requires human approval to modify a database, it pauses the workflow by shifting to an input required state until the necessary confirmation is provided. Treating agent workflows as asynchronous state machines is the only reliable way to manage the unpredictable duration of autonomous reasoning. When the execution finally finishes, the protocol shifts focus from managing the process to delivering the output. A standard large language model typically returns unstructured plain text, but in an automated pipeline, a block of text is highly inefficient for downstream systems trying to parse data. A2A resolves this with the task artifact update event. This mechanism ensures that results are delivered as structured, machine-consumable packages. This artifact is divided into distinct parts. The text part provides a concise, human-readable summary of the completed work. The data part carries structured JSON payloads, like lists of impacted services, while the file part handles generated binaries, like network configurations or PDF reports. By standardizing the output into these discrete parts, A2A ensures that a client agent can deterministically parse and act on the results without risking hallucination. This brings us to a major architectural question. Does the agent-to-agent protocol compete with Anthropic's Model Context Protocol, or MCP? They do not compete. They operate on entirely different axes of the AI interoperability stack. MCP operates on the vertical axis. It is the connector that links a single agent downward to its specific context, local tools, and enterprise data sources. A2A operates on the horizontal axis. It is the network layer that enables entirely separate, autonomous agents to discover each other and delegate tasks. The two protocols are complementary. A client agent uses A2A to delegate a complex task to a specialized remote agent. That remote agent then uses MCP to reach down into its own local databases to execute the work, before returning the final artifact back horizontally via A2A. MCP helps engineers build a powerful individual agent, but A2A provides the infrastructure to build a scalable system of agents. The agent-to-agent protocol dismantles enterprise integration silos, allowing cross-functional workflows without forcing engineering teams to abandon their preferred frameworks. By relying on open web standards and explicit data contracts, A2A provides auditability, security, and composability at scale. As agentic AI shifts from isolated experiments to critical infrastructure, the communication contract between those systems becomes the most vital layer of the stack. A2A provides the networking architecture required to operate a true, collaborative ecosystem of artificial intelligence.